Hi, my name's Dylan, and my space journey began probably when I was just a little kid. I've always been interested in space and rockets and such as you would be as a little kid. And nowadays, what interests me most is just the amount of information out there where I can hop onto YouTube and watch different videos every day of any different kind of subject on space. Well, I think that what I'm most excited for is where we're going. I'm 40 years old, and I'd love to still be here when we finally put someone on another planet. The stuff that's happening right now with SpaceX is so interesting, and the path that they're going on, and I think that the future is closer and closer, really. I would love to see us put a human foot on another planet.
Welcome to Your Space Journey, where we venture into the future of space exploration and the incredible leaders who are taking us there. Here's your host, Chuck Fields.
Hello, thanks for joining me today. Today I'm pleased to introduce my guest, Tom Kacpura. I was fortunate to travel to NASA Glenn Research Center earlier this year to interview Tom, the Advanced Communications Program Manager for Space Communications and Navigations, or SCaN. Now, SCaN provides communication services that are essential to the operations of NASA space flight missions. In fact, coming up with Artemis as we go back to the moon by 2024, you're going to see better video and audio quality for this mission thanks to SCaN. Now, SCaN provides communication support to NASA and non-NASA missions by managing three networks: the Deep Space Network, the Near Earth Network, and the Space Network. Now, Tom, of course, has an amazing background and amazing award-winning history, so of course I asked him how his passion for space began. Here's Tom discussing that.
So since I was born right at the end of the Apollo time, so I actually got to see them land on the moon. I was only 6, but it was that's ingrained in my head and all the excitement of the Apollo era.
Yeah.
And we had somebody in our hometown, an astronaut named Paul Weitz, who was on the Skylab. He was on the second Skylab. So there was a lot of press in Erie, Pennsylvania in 1973 when he was on the Skylab, and so that's always been ingrained in my mind. And I also went to the Kennedy Space Center around the same time, so it was right after the moon landing. They were still doing the Skylab missions. There's a lot of excitement in the country when we were doing those moon missions, and so that's always been ingrained in my head.
Sure.
And so when I went to college, I had an electrical engineering degree, and where I went to graduate school was called Rensselaer Polytechnic Institute.
Right, oh yeah.
And they do a lot of research for NASA. And so when I was there in our labs, you could see all the different research things. And so that was kind of ingrained in my head. And so when there came a job opportunity in order to work here at Cleveland at the NASA Glenn Research Center, I took it because it was, it just that fundamentally was something that was exciting to do.
Now, as I mentioned earlier, SCaN stands for Space Communications and Navigation. Here's Tom giving an overview of the SCaN program.
So the SCaN program, or Space Communications and Navigation Program, that's an acronym for all the work that we end up doing here for doing communications work. Okay? The SCaN encompasses a lot of different things that they do. They do work with the different networks in order to provide communications to our spacecraft that are orbiting the Earth, as well as spacecraft that go out further. And they also do the research for the next generation systems as well. So it's an all-encompassing program from the technologies that make it up to having systems that are maintained that provide the communication network. So it's a fairly healthy program that the SCaN program is.
Now, the amazing thing about SCaN is it actually has its roots all the way back in the 1950s. Here's Tom discussing that.
When they started doing the first spacecraft, so think about back in the Mercury days and the beginning of the whole space program, they needed some way to talk to the rockets that went up.
Right.
It was pretty easy when you were doing just a suborbital flight that just went straight up and came back down. Those systems were pretty simple.
Sure.
But when we started going to the moon, now you have very long distances. I mean, the rough distance, it's a 250,000 miles to go to the moon, okay? So now all of a sudden you start thinking, okay, I need to make a system that's going to be able to talk to it. And think about it, if you need to have coverage all throughout the Earth, because the Earth is rotating, the moon is going around the sun, having those systems that could support that, now you needed a much more intense system in order to support it than what the old systems were that just could support a simple thing that went up a couple hundred miles and came back down. down to the Earth.
Huge difference, yeah.
It was a huge difference. And so those were the initial systems that they built. They had to build systems, and if you think about it, back in the day, when you saw the Apollo missions, okay, there was not a lot of coverage that they had. The coverage was fairly minimal, and even when they landed on the moon, those were pretty grainy images,
Right.
okay? In this day, everybody, it's all visual, right? And you see the internet, you see the power of that capability, now getting a lot of the science information back down to the Earth. What did they do when they first started going from the moon missions, where it was kind of a dedicated mission, into having lots of spacecraft that went?
Right.
They ended up building a system that they called the Tracking and Data Relay Satellite System,
Okay.
or TDRS, we
TDRS,
call
yes.
it. TDRS is it, and they built a number of satellites which are orbited in fixed places around the Earth, and they call them geosynchronous.
Right.
And geosynchronous means they appear at the same place always from a fixed point on Earth.
Excellent.
And so now you have systems that are set up that as the spacecraft orbit the Earth, they can use that and they can talk back to the Earth, and we can get all the data back from all the different spacecraft that we have. And most importantly, we can control those spacecraft as well, because it's very important to be able to keep track of our spacecraft, and then get the data back, because that's a big function of NASA is all that science data that we create. We want to get that back in the hands of the investigators, and they're the ones that'll do the science with that, and they'll do all the understanding of it. And our communication systems that we build, they're very important to getting that science data back to those researchers.
Now, as we mentioned before, SCaN has 3 networks: the Near Earth Network, the Deep Space Network, and the Space Network. Here's Tom discussing those networks in more detail.
There's 3 networks that we have because we've got some unique things that we have to take a look at. We've got satellites that orbit the Earth, because there's a number of different science spacecraft that we have out there, whether they're observing the Earth or whether they're doing some sort of control of some different things that they have out there, as well as they have spacecraft out there that are doing kind of next generation research, like our space station, okay? And so when you look at those platforms, what do you need to do to get that data back down to the Earth? Some of it we send actually direct down to the ground. Some of it we send through our TDRS network. So those are 2 of the networks we have. Our TDRS network we call our space network. And we have a direct-to-ground network for some of our more simple science spacecraft, where rather than going and having all the burden of sending that up all the way up to a geosynchronous satellite, that's 22,000 miles up in space. That's a fair distance. When it's easier to send it directly down to the ground. It's only a couple hundred miles. It puts a lot less burden on the spacecraft. Every pound we launch, it's a lot more expense. So the simpler we can make some of our spacecraft, the more science we can put on those spacecraft. One of the other networks that we have is an interesting one we call the Deep Space Network.
Right.
Okay, and the Deep Space Network has a unique problem. It's one thing to be able to collect the data from satellites or spacecraft that orbit the Earth, because they're fairly close. They're normally typically within a couple hundred miles of the Earth. But you start going out to the moon or out to Mars,
farther,
you start getting some really far distances. And even Pluto, when you start talking going out to, we just had a mission out to Pluto here not
New
that long
Horizons,
ago. It took 18 hours for traveling at the speed of light for the radio data to get back to the Earth.
Incredible.
Okay, and one of the challenges is because you're so far out at that point, okay, those signals that come back are very weak. So we need to build some systems on the Earth that have antennas that can collect that data. And analogy to give to your listeners is that, think of an antenna. You're asking, what is an antenna? And one of the unique things I look at it is like your nozzle on a sprinkler, okay? So if you have it in a way that you have it that's kind of a wide, gentle it's very gentle, right? And it's a kind of wide pattern, okay? So that then you don't need to you get a wide pattern associated with it, but it doesn't necessarily have a lot of force to it.
Right.
But if you squeeze that nozzle, now all of a sudden it's very directed. And so now that's what they do. They come up with very directed antennas, which tend to be very large, so you can collect that energy from those far distances, and then we can get that back and amplify that so we can get those signals back from those distant places that NASA is sending their spacecraft to.
Now, the NASA Glenn Research Center is an integral part of managing these networks. Here's Tom discussing that.
So the Glenn Research Center is a little bit different than some of the other NASA centers. Okay, so when people think of NASA, they instantly think of Houston, where they have our man control centers down there, or they might think in Florida of the Kennedy Space Center, where we launch a lot of our rockets. We have some other places like the Goddard Space Flight Center. They do a lot of science missions, and JPL does our deep space missions, where we send things out to far planetary bodies. Okay, so the Glenn Research Center is a little bit more unique. It's one of the older research centers that are part of the NASA umbrella of research of NASA centers. And what they do is that they are more research and technology.
Okay.
And so rather than operate a network or actually build some kind of key spacecraft, what we end up typically doing is we kind of do the innovative cutting edge kinds of things.
Nice.
We will build new kinds of technologies that have never been done before. And a big part of it is we research those technologies, build up kind of fundamental next generation kinds of things, but then we'll also test them and fly them and do those for the first time. So we kind of have a broad range of activities that we do here. We look at we do work obviously in the communications area. We do work in rocket research, so there we have a lot of fundamental rocket research that we do in terms of the engines themselves. Do a lot of aeronautical research here. We have wind tunnels where we still test airplanes in wind tunnels in order to test them out to make sure how they will go. We do icing research, and then we also do power and propulsion. So we do the electrical power, which is how I ended up started working here. And we also do the rocket power, a lot of next generation engines, whether they're for spacecraft or whether they're for the next generation airplanes. We do that kind of research here.
Now, I mentioned earlier that Tom is award-winning. I really enjoyed my visit. As a matter of fact, Tom was telling me in more detail about how he was recently inducted into the Space Technology Hall of Fame.
Back in about 10 years ago, we were tasked to take a look at next generation radios. Okay, and the task that we were given was had a task that said, hey, we are seeing that everybody's kind of buying their own radio, and we're seeing now that they're all reprogrammable. Radios don't look like radios anymore. They look more like computers. And so why is that everybody kind of is doing their own thing, and if I buy a radio from one manufacturer, I can't reuse it with any of the software that from other radios. So we started putting together an architecture that really kind of like your Windows operating system. Think of a radio, kind of the radio platform looks like a computer. You've got some sort of operating system on it like Windows or the Apple operating system that's associated with it. You've got all sorts of applications that fit into it. And so on our radios, our applications are our waveforms. Okay, so if you're looking at, like, for example, an AM radio, okay, that would be one kind of a waveform, or an FM radio, they have a different, unique waveform that they would have. There should be no reason why you cannot put if you buy an AM radio, put the FM waveform on it, or vice versa, put the FM waveform on the AM radio. Now, when you start looking at a lot of the radios that NASA uses, we do have voice radios that we use for the astronauts in order to talk back to the Earth. However, we use a lot of radios that send data, okay? And so when we do our science data, a big reason for a lot of the research that we look at is improved ways in order to get that science data back to Earth. And a lot of times it's image data, which is basically a lot of bits, okay? It's a lot of data, and how do you get that back down to the Earth? And so one of the things that we were looking at was doing what we called Ka band radios, okay? So Ka band radios, your DirecTV is an offshoot of Ka band radios, okay? And the Ka band radios, that technology that you use in your receivers for your televisions right now, that was really invented here at the NASA Glenn Research Center.
Was it really?
We did what we called the AX satellite that was back in the early 90s. It was late 80s, early 90s, where they demonstrated essentially the fundamentals of how they would do the broadcasting for Ka band radios, and they use that for DirecTV. They use it for a lot of images. All that was formulated here at NASA Glenn Research Center along with our industry partners.
Very nice.
And so now we took a look at that technology that we were finding for the next generation of radios and saying, okay, let's combine the next generation radio technology with the higher bandwidth capability, so that, everybody wants higher bandwidth,
of
right?
Course, yes.
More and more bandwidth. Can't have enough of it. And so NASA would like to have the same thing too. So what we did is we partnered with a number of different manufacturers to build next generation radio. So we did one with the Jet Propulsion Lab out in California. We did another one with General Dynamics, and we did a third one with the Harris Corporation, and it was a new kind of radio. It really was a Ka band radio, but it was software defined. Okay, and so your cell phone is software defined. But one of the big challenges we have is that if you're going to fly electronics in space that you would use for a radio, fortunately it has to be very radiation tolerant.
Yes.
And those, if not radiation tolerant, all those particles that are out there, they'll basically corrupt a radio pretty quickly, and they'll destroy it if it's not built properly. So we built the next generation radio, and we demonstrated it on a payload we called the SCaN test bed. We put that up on the International Space Station, and we flew it for 7 years. Wow. Okay, and so this was a big accomplishment for us. It was a fairly large effort in order to put a platform together that flew on the outside of the space station, tested these 3 new radios and all. We tested out how to reprogram them, how to send the data through them, how to basically do a number of different things that would show how those radios would operate for our next generation of missions. But a key part of it was that we flew this next generation Ka band radio, and this was the first one that had ever been flown as a software-defined radio. Wow. Okay, and so when we, as we started to do that, tested it out and operated it for a couple of years, we were nominated for the Research and Development Top 100 Innovations of the Year. So that was back in 2014. Wow. And then in 2019, we were nominated for the Space Technology Hall of Fame. And the reason for that was that not only what we had done in terms of flying that first Ka band radio, but all the spin-off applications that had come on that afterwards.
Now, one of the aspects of NASA that's always amazed me is just how many spin-offs we get from the amazing innovative technology. Here's Tom discussing the NASA spin-offs.
And so when you think of NASA and spin-offs, people think of Velcro and Tang
exactly,
and all that.
Yeah.
But there are a lot of innovations that go on because NASA's really plugged into a lot of the fundamental technology that this country is built around.
Right.
And so when we start looking at what they did with our Ka band radio after they used it, so the first thing that they did is they built a system that they could track airplanes with, okay? And so when you look at airplane tracking, typically you see at an airport, you see the radar spinning around, right. Okay? And so what they did now, looking at space-based radars, now you can see things that are much better than what you had before. So our Ka band radio, which we had used as a data radio in order to send images back from the space station, now all of a sudden it can also serve not only as the radio, but it can serve as the sensor that can do all the imaging of all the airplanes on there. So they put them on. They put 81 of them on the Iridium satellites that we have out there, and that's the basis for the basically worldwide tracking of airplanes today. Okay, so that was the first thing that they did with that.
That's incredible.
Then they built a number of different spin-offs of that kept going even further because they used that same platform that we flew on the space station for 7 years. And they looked at being able to track greenhouse gases, so there was a Japanese payload that they used that for. They built another payload that was a series of satellites that they flew that do shipboard tracking, because before that, the only ship tracking that they had for all the maritime stuff was basically land-bound, and so they had nothing looking at any of the ships out there other than they had to use satellites that weren't designed in order to do that, to do the tracking. Now all of a sudden they had a dedicated system that could do shipboard tracking.
Amazing.
And so if you think about some of the benefits of things like that, for example, with the system that they use for the aircraft tracking, we had that Malaysia airplane that was lost here a few years ago.
Right.
Had they had the tracking system in place in there, then they would have had active tracking. And so odds are that they would not lose airplanes like they had just a few years ago. So there's a number of things at the change of just a basic computing platform that we can fly in space. The spin-offs, they've used it for a number of different things. And right now we've kind of come full circle, because now the next thing we're using this for is that we're working with the DoD to launch a new satellite, and that'll have a optical communications system on that.
Really?
Okay? And so the benefit of an optical communication system is that, remember I was talking about the nozzle being able to concentrate very fine, the beam on this. So if it's a RF or a radio frequency based one, you can get it pretty fine. If you use an optical system, you can get even finer. And so the data rates that you can get out of those optical systems are much higher than what we can get out of some of the RF systems we have now. But the RF systems are still going pretty good now, so we actually are putting an RF system on that, and we're going to put a latest and greatest version of our Harris radio, and we're going to fly that on there. And it's smaller, it's lighter, but it has more features than what we just had just a few years ago. We're trying to look at a number of different applications that we're using this terminal for as well as we go forward.
Now, we're all excited about Artemis, the plan to return astronauts to the moon by 2024. Well, SCaN's going to be an integral part of that. Here's Tom explaining how.
Like most of the agency right now, we are gearing up for doing the next generation systems that we need to do to land the man on the moon woman on the moon, first woman on the moon in 2024. So that's very exciting. And so a lot of the systems, we're looking at these next generation systems, and a big part of it is that having improved communications from what we had with the Apollo missions. I mean, having full-time coverage, being able to send all the data back in real time and be able to observe all that, that's a big part of what we're trying to do. Here at NASA Glenn, we're also building basically the gateway system, that we're building the first module that goes on the gateway that will have a communication system associated with it. But also we're looking at some of the relay satellites that will go around the moon, so that when we have either astronauts on the moon or some of the assets on the moon, now they'll have some relays right above the moon so that they can talk to those relays, similar to how we have them around the Earth. Put that infrastructure in place, and that'll support our communication needs as we go forward. So that's a big part of what our next, the focus is for SCaN.
Now, of course, going back to the moon this time, we're going to have hopefully a lot better quality than a 1960s black and white image on a TV screen. SCaN is going to help get better audio, better video this time. Here's Tom explaining that. You mentioned at the beginning of the program how at the young age of 6, 7 years old, you remember astronauts on the moon. So this time around, if we have quality video coming from the moon and probably nice audio where we won't question the words that are being said exactly, we'll be able to hear clearly, that will be due to the efforts of SCaN.
It will be due to SCaN.
How's that make you feel?
It is a good feeling. I mean, in order to see, it's always nice to see tangible efforts come out of it. And so a big part of the work that we do, there's a lot of work behind the scenes in order to put anything in space. But when you have opportunities like that to be in the public eye and to see something like that, then see it happen. I mean, it's 50 years since we've basically been on the moon.
Right.
And so now to see that happening again and see that excitement, I mean, I see a lot of excitement out there. When we had the 50th anniversary last year of the moon landing, there was an excitement about NASA that I haven't seen in a while. And so seeing that happen in terms of, now we're seeing the commercial side of this, and people are flying things in space. You see universities now fly payloads that you never saw before, but now to take a look at it and look at now to the moon and beyond, I mean, the goal is not just the moon, right? But it's actually to go to Mars and be able to continue on going forward. And so we're actually seeing a push now in order to continue that vision that was started a number of years ago when NASA was first started.
And that's going to be incredible, right? Pictures from the moon,
I think so.
Pictures from Mars. Tom, I want to congratulate you and your team on just the awesome work so far. I want to thank you for taking time to join me. I really appreciate it.
Because it's really a team effort that does this. It's not one person. When you see a couple of people that are out there, you know that there's a huge team behind just about every effort that's of something that flies in space, and so that is greatly appreciated.
Excellent. Thanks again for joining us.
Thank you.
Your space journey.
Well, I really enjoyed my trip to NASA Glenn, and I just want to thank their entire team for welcoming me out there. I want to thank Tom for joining us today and discussing the SCaN program. If you'd like to learn more, just go to their website at nasa.gov/SCAN. Again, I want to thank NASA Glenn for their hospitality. I want to thank you for joining us today. We really do appreciate it. If you can share this episode with a friend, we'd appreciate that too. We'll see you next time. God bless.